Hi, thank you for giving me the opportunity to give a lightning talk. My name is Eleanor, and I'm a fourth year PhD student at University College London, where I work on quantum computer hardware, and I also have more recently been working on quantum computer software with IBM. I'd like to give you some context before telling you about my research, where we propose an entangling gate, which does a 2 quantum bit entangling gate, which does not require precise fabrication techniques like the current ones do, and which has a higher probability of success and which requires less tuning. Why do we care about quantum computers? Well, there's a lot of quantum chemistry simulations which enable us to find new materials for batteries, carbon capture materials, efficient fertilizers, drugs, protein structures. Essentially, quantum computers have access to a different complexity class than classical computers, the bounded error quantum polynomial class, not unlike just polynomial time problems that classical computers can solve. And this enables us to optimize problems with supply chains and logistics or related to financial portfolios. And ultimately, it enables to understand how our universe behaves at the atomic and subatomic levels. Well, how do quantum computers, how do we use them? We use them on a classical interface, and this is the IBM Quantum Experience Circuit Composer, where anyone for free can create a quantum circuit using gates and run it on a real computer. Just a quantum computer requires gates, just like in a classical computer you have AND, OR, NOR, XOR, and so on. In a quantum computer you also require gates. And the Qiskit language is open source, and what's special about it is it's applicable to any type of quantum hardware. There's different types of quantum hardware. There's silicon, superconducting qubits, ion traps, cold atoms, you name it. There's lots of different ways of controlling quantum bits and entangling them. So how do they work, quantum computers? What's really key? What are the key items for quantum computing? Well, two of the main ones are entanglement and superposition. What is a quantum bit? How does a quantum bit make use of superposition to begin with? Well, a classical bit has 0 and 1. A quantum bit, or heads and tails, has in the superposition of 0 and 1 until you measure it and you collapse the state, and you can then only read out 0 or 1. It was tails. So you probabilistically, by making many measurements, then find out what the actual state was. In silicon, in the platform which is silicon, which is what my research is about, you can have a silicon atom, which is a black dot, connected with electrons to other silicon atoms. And if you replace a silicon atom with a phosphorus atom, it's got an extra electron compared to the other silicon ones. That extra electron has spin and is a quantum item which can make use of superposition. What's something else which we really need for quantum computers? We also need to make use of entanglement. Entanglement is if I create an entangled state between two quantum spins, it's difficult to create the entangled state, which is what requires an entangling gate, but the entanglement enables me to, if I create the state, measure one and know without looking what the other one is. However far apart I've put the other one, it doesn't matter. I know from one what the state of the other one is. So how do I make this very important gate in silicon? I can control the electron by shining light on it. And if I shine light on two phosphorus donor electrons at the same time, they both try to absorb the light and expand. That's fine if they're far apart, but if they're close together, they can't do that. And that is called the Rydberg blockade. This way, we correlate the electrons. We try to shine light on them, and their behavior is correlated because they can't both expand at the same time. And this entangles the electrons. And this means they only need to be within a certain distance, and they will get entangled. So using the Rydberg blockade, we've created a gate which requires less tuning and has high fidelities and is distance independent. I hope you enjoyed the introduction, and that you know a bit more about why we care about quantum computers, what the different types of platforms are that we can use them on, and what the two core concepts are, and that we created a new type of entangling gate. I'm called Eleanor, and I would really like to contact you or talk with you if you're interested to hear more or learn more.
Great, Eleanor, thank you very much.